proceed to this lecture, I want to ask if you guys are hearing me clearly. Are you guys hearing me clearly?
Yes.
Okay, thank you so much. So I'm actually gonna walk you through. Can you see what I'm projecting right now? So can you see what I'm projecting right now?
Yes.
Okay, so today we're going to start another a very special topic that I call Introduction to Poisson Regression Model. But you know what? I'm actually want to review what we've done before. Okay, I could remember when we started this course at the beginning of this semester. I we started, you know, from simple linear regression. Like I said, we are in a world where we may actually want to, uh, build a model to be able to explain, in an attempt to explain relationship between variables and in such a way that one variable can be predicted, uh, using information available about the other variables. And because of that, if we really want to do that, there are different kind of regression. There are different kind of type of regression models that can be actually be fitted. Okay, depending on the true relationship between the variables. I could remember we started from simple linear regression. Uh, with fixed linear regression, there's an assumption where there's an assumption that a straight line relationship between a continuous response variable and uh, you know predictor, one predictor. Okay, and on simple linear regression, of course, you know how we examine the model, how we evaluate the model. We started by estimating parameters in the model, and after the estimation of parameters in the model, we try to subject the model to diagnostic testing. Okay, I walk you through from the process of, you know, uh, estimating the parameter of the simple linear regression model. Not only estimated the parameter, we estimated the point. That's what we call the point estimate of the parameters. We also do the interval estimation of the parameters. And I could remember we also tested, the parameters of the simple linear regression model for significance. Not only that, I also walk you through, you know, evaluating the significance of the overall parameters in the model by using F-test. Okay, and from there, we try to investigate assumption underlying the use of simple linear regression model, where we try to investigate the assumptions of linearity, we investigate the assumptions of normality, we investigate the assumptions of homoscedasticity that I call the constant variance, and so on like that. And not only that, we also investigate whether there's going to be an unusual observation in the data point. Okay, we also investigate whether there's going to be high leverage. Of course, well, I introduce you to a Cook distance. Okay, and of course, you know how to do that. And along the line, when there's a violation of assumption, of course, I introduce it to what we call a power transformation, okay, we did transformation in a situation whereby we realize that the relationship between the variable under investigation, linearity assumptions have been violated, and if other assumptions is violated. And after that, I extended that to a situation where we have a quantitative response and a categorical predictor, the one I call a domain regression model. And after that, we move from the idea of that to multiple linear regression model, where I, we introduce, we work on more than one predictor in a model. Okay, I walk you through the multiple linear uh, regression model, and we actually do the same. Okay, we go from the estimation of parameters in the model to the testing the significance of the parameters in the model, to model selection, to a situation where we're trying to add variable into a model and trying to test that for the for significance. Okay, so we did a lot of stuff. Okay, now we did a multiple linear regression model, and from the multiple linear regression model we also moved to a situation whereby we consider interaction. Okay, model with interaction, where we are able to model we're able to test the effect of main effect and interaction effect. Okay, and then from there we consider a situation whereby uh, the nature of the response variable is categorical. And when the nature of the response variable is categorical, of course, what I remember we did last was that, okay, we're actually going to apply logistic regression model. Okay, when the response variable is categorical. Okay, when the response variable is categorical, we apply logistic regression model. And you know what? I walk you through simple logistic where we have one categorical response variable and one predictor, and I also walk you through multiple logistic regression model where we had one categorical response and as and as many and different kind of predictors. Okay, where predictors could be categorical, predictors could be the combination of a categorical and quantitative. Okay, so why I'm trying to, summarize what we have done before is just for you to be able to know the right model. Okay, if you want to fit a regression model to data set in an attempt to study relationship with an attempt to predict, you know, certain response from a given levels of predictors, you actually need to know what is the right regression model, what is the appropriate regression model am I going to use, because there are different kind of regression model. And you know what, these regression models are problem specific. Okay, they are problem specific in the sense that you actually need to use the right regression model, in an attempt to fit relationship among variables. And let me tell you something. The reason why at times in the world scientists or researchers don't get things right is simply because maybe we are using inadequate regression. Okay, we're using inadequate type of regression to fit relationship. Okay, and don't forget, we find ourselves in a world that is stochastic in nature. Okay, the world is stochastic in nature because there's a variation here and there, and as a result of that, we actually want to capture this stochastic phenomenon, okay, using the model. And the fact remains that the model we're using cannot actually capture reality. Okay, I'm going to say that again. The model we're using cannot capture the exact reality. Okay, as scientists, as researchers, we do not have a perfect control of the world. I'm going to say that again. We do not have a perfect control of the world, because of the fact that the models that we're using, it's an approximate reality. Okay, the model that we're using cannot really capture 100% of the reality. Okay, but you know what? According to Judge Box, Judge Box said, and I quote, "All models are wrong, but some are useful." Okay, all models are wrong, some are useful. Those ones that are useful, are those ones that we have been able, to investigate for adequacy, and we realize that they are good and they are actually giving us what we want. So as a researcher, I think what we actually need to do is to be able to figure out what is going to be the right regression model that I'm actually going to fit for, for my data set. Am I going to fit a linear regression model? Am I going to fit a logistic regression model? Am I going to fit a dummy regression model? Am I going to fit a model, regression model that has to do with the interaction? Am I going to fit a logistic regression model? Am I going to fit a Poisson regression model? There are different kind of regression model, so we need to figure that out. Okay, like I said, the regression model here are problem specific. Can you guys hear me?
Yes.
Okay. Thanks for confirming that. So today, so having reviewed the background of what we've done before, today we want to have a new regression, and this regression can actually be called Poisson regression. Okay, now the question now is, when can I use Poisson regression? Okay, I'm actually going to walk you through that today. Okay, so but you know what, I'm actually going to have a brief introduction about Poisson distribution. Now, can you guys see this now? Why can't data? Can you see that now? Uh,
Yes.
can- okay, okay. Thank you for that. Let me tell you this. Because we want to talk about Poisson regression model, I need to walk you through what we mean by Poisson distribution. Okay, there are different kind of probability distribution. We got a normal distribution, we got a binomial distribution, we got a gamma distribution, we got a Poisson distribution, and so on like that. But right here, we're talking about Poisson regression, okay? If I really want to know, you know, when to apply Poisson regression model, I think we need to first understand the Poisson distribution, and we need to understand, the data set that are distributed according to Poisson distribution, okay? And that is the reason why I want to walk you through this right now. Okay, so let me confirm to you. When I say Poisson distribution, is a probability distribution for Kant data, okay? Kant data, okay? Let me give you an example of a Kant data. Number one is a number of traffic accident per day, okay? In the state of Illinois, in the city, particularly when you consider the city of Chicago, you may actually want to, you want to count, you want to know the number of accident, accident, due to traffic, the traffic accident in a day. And let me tell you something, when you take a look at accidents, accident is not something that is pleasant, okay? It's something that occurs once in a blue moon, okay? Now, it's a random phenomenon, okay? It's a random phenomenon, okay? So the question is, the number of traffic accidents in a particular city, actually follow a Poisson distribution, okay? Because it's a rare event, okay? It's an event that occur once in a blue moon, okay? And that is the reason why, when you want to talk about, a Kant data based on that, of course, the probability distribution to figure that out is Poisson, okay? I'm not talking about Poisson, okay? Take a look at what I say right here. I'm talking about Poisson, okay? Not, look at that, I got the double X, Okay, it's not something poison. It's not poison. Okay, it's not poison that can actually kill. Something that they used to kill a rat or something like that. No. So this is a poison. Okay, double X. Okay, so give me 1 second. Like I said, uh, I want to show you. We're trying to talk about, why count data. Okay, we talk about the number of traffic accident per day. We talk about the mortality count in a given neighborhood per week. Okay, these are unpleasant situation. Of course, we don't expect people to just, to just die like that. We don't expect a good number of people to die in a particular neighborhood in a week. Okay, so if you're looking at the mortality count, okay, of that, then we can also look at the number of coughs in a concert hall per minute. When I go to a concert hall, okay, a concert hall is actually going to be crowded. Okay, so can I count the number of coughs, okay, per minute? Okay, you know, the way people cough, okay, because it's something that is contagious. I think you know that. Okay, so can we have an estimate, okay, of the number of coughs, per minute? Okay, so how do this actually follow Poisson distribution, because it's a random process. Okay, people don't just cough. Okay, they actually cough, or of course, if they are unpleasant, they found themselves in a kind of difficult situation attributed to it. Okay, just like what is happening right now, that we're in the middle of pandemic. Of course, when somebody sees somebody coughing, I know some people were actually going to be maintaining social distancing. Okay, so the question now is, in 1 minute, how many coughs can we have in 1 minute? Another example of a count data is when we talk about the number of customers arriving in a shop daily. Okay, you take a look at Walmart, you take a look at Target, you take a look at other grocery stores. Now the question now is, how many customers are we going to have in our that we're going to have in our shop? Okay, how many customers are we going to have in our restaurant? Okay, because you know why? Why do I need to know? Okay, if I have a grocery store, of course, I actually want people to come and buy something. Okay, and you know what? People actually come from an infinite population. People come randomly. Okay, at times, I as a customer, okay, if I may decide, maybe I don't have it in mind to visit the grocery store. Okay, and maybe I check my kitchen, and I realize that, okay, I actually need some sugar, or I need some salt or stuff like that. Of course, I may decide to go to grocery store, okay, to buy that. Okay, so which means the appearance of customers in a shop, in a store, okay, is random. Okay, so the question now is, since this is a random phenomenon, how many number of customers am I likely to have in my shop in a day? Okay, so that is also an example of a count data. Okay, so another example I'm actually going to give you right now. You can look at, we are in the middle of pandemic, okay, COVID-19, or where you know what do I call it? The officials of every country are trying to figure out the number of COVID-19 cases, okay, per day. Okay, so this is also because that's a random phenomenon. Okay, so how many COVID-19 do we have in this day? How many COVID-19 do we have in that day, and so on like that? Okay, so this fall under the example of count data. Okay, so the next thing that I actually want to talk about now is to give you the overview of what we want to do. Okay, so like I said, uh, the logistic regression model, the linear regression model that we have done before may not be appropriate for count data. Okay, but you know what? Logistic regression, at times, logistic regression model, we use it you know, in modeling count data, okay? But that is actually going to compete with a new model that we call Poisson regression model, okay? So at times we use logistic regression model as well, okay? So take a look at what I have here. Like I said, so far, the regression strategy we have discussed allow us to model the expected values and the expected increase in linear regression. I think you know that, we've done that, okay? Then the log odds or the log of odd ratio have also been, you know, talked about in logistic regression model. But do you know something that we have not really done before, okay? And why we need to actually talk about it is we actually want to model counts, okay? And in modeling counts, we're going to be talking about incidence rates, okay? The incident rate. You know, it could be the incident rate of a disease, okay? With the COVID-19 that is going on in the world, we may actually want to know the rate of transmission, okay? We may be interested in the rate of transmission of this disease, okay? We actually want to know, we may actually want to compare the rate of COVID-19 in both male and female, okay? We may also want to, you know, compare the incidence rate of this disease across countries, okay? So, well, when we want to achieve anything that has to do with the incidence rate, of course, we actually going to be thinking we need a new model to be able to figure that out, okay? And if you want to actually look into that, you actually need a Poisson regression model, which is actually the model for counts. And not only that, we are also interested in, you know, talking about the incident ratio, okay, when comparing across levels of a risk, okay? So this is what we're actually going to be doing here, okay? So if your research is about modeling counts, okay, then today's topic, what we want to do today is very, very essential. Okay, so what I want to do right now is just to walk you through what we mean by probability, by Poisson probability distribution. If a random phenomenon, okay, you know, if how do we model, you know, how do we recognize the probability distribution of a count data, okay? If we have a count data where, you know, something occur, you know, in an interval, okay? The other time we're talking about what is going to be the number of customers that will visit my grocery store in a day, or what is going to be the number of cups are we going to have in a minute, in a concert, or and stuff like that. Of course, what is the probability distribution, you know, the mathematical architecture of that distribution is what we have right here, okay? So this is what we call Poisson distribution, okay? This is what we call Poisson distribution, okay? So the probability of X occurrence of an event, okay, in an interval, okay, the probability of X occurrence of an event, okay, what if an event occur in an interval, okay, so this is the probability of you know, probability distribution of that, okay? So where X is actually going to be number of occurrences, okay? It could be 0, it could be 1, it could be 2, and so on like that, okay? I want you to know there was a time that every country has a 0 cases of coronavirus, okay? A 0 cases of COVID-19, okay? From there, it jumped to 1, it jumped to 2, and so on like that, okay? So those are random phenomena and that changes with time, okay? So the lambda here is the expected number of occurrences in the interval, okay? The lambda is more or less the mean, okay? The mean, okay? So the expected number of occurrences in the interval, and the E right here, of course, is a constant, okay? Is that, okay? So what I'm talking about right now is what we call Poisson distribution, okay? And the Poisson distribution is the probability distribution of a count data, okay? Is there anyone who want to ask question based on what I'm talking about now? Is there anyone? I want to believe that you guys are hearing me, right? Are you
Yes.
okay? Okay. Somebody said yes. Okay, I'm looking at my chart right now. Somebody said, what does the exclamation represent? What do you mean by the exclamation? Exclamation. Which of that? Which one are you talking about right here? Oh, somebody said it is the factorial. Okay. I think he got it now. Okay, so if you take a look at what I have here, okay, this is a Poisson distribution, okay. This is this can be used to figure out the probability. Okay, what is the probability that there's going to be zero number of accident? Okay, so what is the probability that there's going to be one accident? Okay, what is the probability that will be two number of accident? Okay, or what is the probability that within the interval of this, what is the probability that I'm going to have, five people will be tested positive for COVID-19 and so on like that. Okay, so this is a distribution that we're actually going to use to figure that out. Okay, so but there's something I wanted to take note. Every probability distribution actually have mean and variance. Okay, so the mean and variance of a Poisson distribution, they are the same. Okay, the mean and variance of a Poisson is lambda. Okay, and the lambda right here, okay, the lambda right here is actually the expected number of occurrences, okay, in the interval. Okay, the average number of occurrences in the interval is what we call lambda. Okay, and for Poisson distribution, the mean and variance are the same. Okay, so and you know what, uh the mode, okay, it's going to be floor lambda. Okay, it's going to be largest, largest integer less than lambda. Okay, so the mode is not likely to be the same as that, but we are not interested in that. We are actually interested in the mean and variance. Okay, so therefore we can say that lambda is the only parameter of a Poisson distribution. Okay, if I want to figure out, if I want to obtain the probability of occurrence of an event, okay, in an interval, then I need to be given lambda. Okay, therefore lambda is a rate parameter. Okay, is a parameter of Poisson distribution. Okay, so I need to be given that, or I need to estimate that if I want to, figure out, the probability of, or the occurrence of an event in an interval. Okay, so understanding that right now, what I'm going to do is that, I told you the other time that if I really want to model something that has to do with the count, where the interest is basically on incidence rate and incidence ratio, Poisson regression will provide us with a framework to handle count properly. Okay, so not logistic regression, the Poisson regression will actually do the job properly. Okay, but in some situation, some people can still use logistic, but you know what, logistic may not be able to answer the question that has to do with the incidence rate adequately. Okay, so the other time I gave you the probability distribution Poisson, and I told you that the parameter under investigation is lambda. Okay, the rate parameter, okay, is lambda, and the reason why we actually going to be using Poisson regression to model incidence rate is because Poisson regression actually have a rate parameter. Okay, logistic regression actually have a rate parameter, and that is the reason why we actually going to use Poisson regression, to model any data, a data, to figure out a situation where the interest is on getting the incidence rate. Okay, because there's a rate parameter in Poisson distribution, and that is the reason why we'll be able to do that. Okay, so what I just want to showcase right here is for you to see the expression, the histogram, of a probability distribution of a random variable, given lambda equal to 5. If I come back to this side now, if I come back to the formula right here, I'm going to show you the formula now. Okay, so if I come back to this formula, if my lambda equal to 5, if my lambda equal to 5, okay, if my lambda equal to 5, then I can determine the probability of x equal to 0. I can determine the probability of s equal to 1. I can determine the probability of s equal to 2, and so on like that. Okay, when I determine that, then I can plot. Okay, you're going to see what I'm going to have right now. So if I'm going to plot the probability. Okay, take a look at what I have right here. I'm actually plotting the probability against 0, again when the number of occurrences is 0, 1, and so on like that. Okay, so that what I have in the horizontal axis here is just the number of occurrences, and what I have here is just the probability of the associated with that. Okay, when lambda equal to 5. Okay, look at the shape that I have right here. What does it look like? Okay, it's looking like more or less like a normal, but it is not normal because you got a long tail. Okay, so this is skewed. Okay, so this distribution right here is skewed. Okay, so Poisson distribution, this is an evidence that Poisson distribution is highly skewed. Okay, it's skewed. Okay, now another thing that I want you to know is that, do you know that from linear regression model, we transform a linear regression model to give us a logistic regression model, okay? And you know the probability distribution for logistic regression model is binomial. I think you know that. Okay, so do you know that I can actually go from binomial to Poisson distribution, okay? And you know what? Because if I'm able to derive a Poisson distribution, and that is actually going to be the distribution for my Poisson regression model. Okay, so what I'm just trying to show you right here is that Poisson distribution can be used to approximate a binomial distribution. Okay, so in a binomial distribution, if you remember what we did under binomial random variable, a binomial random variable is a variable that can actually that is a dichotomous in nature. What do I mean by dichotomous? Okay, that has two levels. Okay, yes or no. Okay, true or false. Okay, you have the disease or not. Okay, male or female. Okay, so stuff like that. Okay, that's what we call it. Okay, so if the sample size is large, okay, and the probability, okay, p here is the probability of success is if it is very very small. Okay, if the sample size is large and the probability of success is very small, then the combination of n and p, which I call n multiplied by p, will be the same thing as, will be equal to lambda. Okay, and you know what? It is the same lambda that I'm talking about that is a rate. Okay, it is the same lambda that I talk about that is a rate parameter in Poisson distribution. Okay, I'm going to show you right now the particular lambda that I'm talking about, the lambda right here. Okay, that I call the rate parameter. Okay, so what I'm trying to say is that you know, binomial distribution, when the sample size is large and the probability of the characteristics of interest is very very small, then when I multiply n by p, it will give us lambda. Okay, n by p will give us lambda, and lambda here is fixed, and lambda here is a rate parameter. Okay, now let me tell you this. What do I mean by n is large? Do you know that if I want to count the number of accidents in my street, okay, if I want to count the number of accidents in my street, there is possibility that I may be there for 5 years and I don't see any accident. Okay, so it means and you know, before I can see an accident, it may take forever. Okay, it means the n is large. So which means the probability of, you know, of seeing an accident, okay, the probability of getting an accident in that situation is actually going to be very very small. So in a situation, and that means that's a rare event, okay? That is something that I'll call in a blue moon, okay? So in that situation, the combination of n and p, we're actually going to be a lambda, and the lambda is the rate parameter, okay? So that is the reason for that, okay? Now the next thing that I actually want to talk about now. So we've talked. If you take a look at what I have right here, now we actually want to investigate lambda. We want to look at the distribution as lambda is increasing. Okay. The other time I used lambda equal to 5, you saw the shape. But now when lambda equal to 30, look at what I have here. It's looking like a normal distribution. Okay. Okay. So it means so. And before before lambda can be equal to 30, okay, before lambda can increase, it means you are working with a large sample size. Okay, it means you are working with a large sample size. Okay, so what I'm trying to show you right here are different values of lambda, a different value of rate parameter. Of course, you can actually, if you want to determine the probability of the occurrence of an event, of course, it's going to be different. Okay, it's just like what we are facing in the world right now. If we were to, for you to be able to obtain the probability that somebody in a community will have a COVID-19, then that depends on the incidence rate. Okay, the incidence rate of a particular community, with respect to COVID-19 may be different from incidence rate of another community, okay? So, and that is what we're trying to talk about right here. Okay, so if you take a look at this example right now, we want to talk about the yearly cases of esophageal cancer. Okay, we actually want to have an example on a cancer in a large population. Okay, example of a cancer in a large population. Oh, can you guys hear me?
Yes.
Okay, thank you so much. Now, we want to talk about a cancer in a large population. And this time around, we're going to be talking about yearly cases of, esophageal type of cancer in a large city. Okay. Now, we want to investigate 30 cases, which was observed in 1990. Okay. Now, the probability that S equal to 30, okay, the probability of S equal to 30, I'm talking about 30 cases, okay? The probability of having 30 cases of that, okay? The probability of having 30 cases of that, then I'm actually going to plug in 30 into that, my model. Look at what I have right now. So it means if I want to figure that out, I need a lambda. What is lambda? The lambda is actually going to be the incidence rate of this type of cancer. I'm going to say that again. And that is the reason, if I want to get the incidence rate of this type of cancer, then I need to know yearly average of number of cases of esophageal cancer. Okay, can you see that now? So it means if I want to determine the probability of having a case, okay, if I want to determine the probability of having a case of a particular disease, then I need to be able to, I need to have obtained the incidence rate of that, okay? And the incidence rate is actually going to be the yearly average number of cases of that, okay? And that is, some of the countries or some of the states that are not getting things right, right now, in the case of COVID-19, is because they're not able to get the accurate number of the incident rate of the disease. And I want to confirm to you right now, the WHO is not really doing their job very well, because I've watched a lot of information from the World Health Organization as regard the COVID-19. They have not been consistent. I'm going to say that again. The World Health Organization has not been consistent with information they are, coming from them. At time they're going to come up with this kind of one form of information. At the, another time they're going to give a different information that is not consistent. Okay, and that is the reason why. That is one of the reason why the world is actually experiencing, the the high number in cases of the COVID-19. Though we also have, some other factors, but this is one of the factors because the World Health Organization, they actually need to lead, okay? They need to lead us very well. They need to give us the accurate information. They need to have an expert that understand, the nature of disease, the incidence rate of disease, so that, the information that we want to get from them, because it's what we actually going to be. That is what we're going to be using as a guide. Okay, we don't want a situation whereby we're going to receive one information today and tomorrow is going to they're going to receive a different information that is not consistent. Okay, so right now, although the World Health Organization, they are really doing they are doing fine, but you know what, in recent time there have been a lot of inconsistencies from them. Okay, so they've not been consistent. Okay, so what I'm just trying to tell you right now is just that, okay, if I want to know the probability of, the number of cases, okay, if I really want to determine, if I really want to have an accurate measurement of that, then I need to be able to figure out, am I using the right incidence rate? Okay, so that is the reason why I said right now, the World Health Organization, what is coming, they have not been consistent with information they are supplying the world. Okay, so another example that I want to talk about right now is belief in afterlife. Okay, belief in afterlife. Okay, a survey was conducted, a general social survey was conducted in 1991. Okay, where men and women were asked whether or not they believe in afterlife. What do we mean by afterlife? Afterlife is just that, okay, when we die, as human being, okay, so is there something like, people have been talking about heaven, people have been talking about different kind of stuff. Okay, so is there going to be afterlife? Okay, that was the question that was asked in this general survey, okay, that was conducted in 1991. Okay, and you know what the possible responses were? Okay, so yes, oh no, or unsure. Okay, so for the purpose of analysis, uh, you know, no and unsure were grouped together. Okay, no and unsure. So no is N, unsure is U, and yes is Y. Okay, and we ask this question across individuals, okay, men and female, and what you can see right here is just that for out of it means 1091 was actually the number of respondents in this survey, 1091, and out of the 1091, 810 people 810 people say yes, there is afterlife. Okay, and 281 out of that say no, or they are all unsure. Okay, and the 435 right here is the number of male, number of men that say yes, there's afterlife. And 147 is the number of men that said no or unsure. So that the total number of men in this survey is 582. The total number of female in this survey is 509. And the number of female, the number of women that said yes, that there's going to be afterlife is 375. And the total number of female that said no or unsure is 134. Okay, so I think you can see this is the result. Okay, this is the response. Okay, now the next thing now, based on what I have, right here, we can actually investigate whether the rate of yes, whether the rate of yes in men and women are the same, okay, we can actually investigate that, okay, whether the rate of, the rate of yes, okay, the rate of yes, okay, the rate of the incidence of yes, okay, we're talking about incidence of yes, okay, we can actually compare, well, whether that is the same, okay, among gender, okay, we can actually work on that, okay, and if we want to work on something like that, we may actually going to use a Poisson regression model. Okay, so now based on the data set that we have right now, I want you to take a look at something. We are still on the data set, okay. Now we are still under the data set of belief in the afterlife. So, a general sociology survey that was conducted in 1991. Now, under an independence model, the probability of belief in afterlife for both gender will be estimated as this, okay? If I want to get the probability of belief in afterlife, it's actually going to be how many of the respondents actually believe in afterlife, okay? If I want to take you back, how many of the respondents believe in afterlife? The number of respondents believe in afterlife is 810. Because 810 respondents say yes, they believe in afterlife, okay? So what is the probability associated with yes in general, okay? The probability of yes in general is actually going to be the number of yes, okay, in the survey divided by the total number of respondents, okay? And that is why we got 810 divided by 1091. So which means the probability of belief in afterlife is actually going to be 0.742. Is there anyone who have a trouble time, figuring out the probability of believing afterlife based on the data set here? Is there anyone? Okay, so the idea we're using right here is just the idea of a probability theory, okay? Because the probability is a ratio of the number of the number of favorable events, to the number of sample space, okay, and the number of the characteristics of interest, because we are actually the characteristics of interest is the number of people who believe in afterlife, okay. So that is what we have right here, okay. Now after having this right now, then do you know that we can calculate the expected count? Why do we need the expected count? Of course, the expected count is actually going to act as lambda, okay? The lambda, the one I'm going to call the incidence rate of that. Okay, so now if I want to calculate the expected count here, now the expected count is actually going to be equal to n multiplied by p, okay? Now, if I want to find the expected count, that is the expected number of male answering yes, if I want to know that, it's actually going to be the number of men asked multiplied by this probability right here. Okay, so how many men do we ask a question from? 582. You can go back to the table. How many men do we have here? We got 582, okay? So we're going to multiply the probability that we just find right now by 582, and that is going to give us 432, okay? It means 432 actually said yes. 432 men actually said yes, okay? If you want to figure that out, you want to check from the table, take a look at that. The one from the table here is an observed, okay? This is 435. The 435 here is actually an observed value of men that say yes. But what I calculated right here is not an observed, it's an expected. I'm going to say that again. There is a difference between observed and expected, okay? This is an expected, okay? So we got this one from expectation, okay? And you know how we figure that out. Expectation will be different from observed, okay? But you know what? The essence of research is to be able to measure discrepancy between what is observed and what is expected, okay? What was observed in the general sociology survey conducted in 1991 was 435 men that said yes, there's going to be afterlife, okay? But the expectation, when we calculate the expected value of that, we got 432. So the same thing also applicable to female. The number of, you want to figure out the expected value for female answering yes, it's going to be the number of women multiplied by that same probability, and that will give us 378. And you know what? If you go back to the observed for women, okay, the observed for women is 375, but the expected for women is actually 378. Okay, just to be able to tell you there's a difference between expected and observed. Okay, so based on that data set, what is our goal? What do we actually want to achieve? And this, you know, there's always going to be a research question, okay? The research question here is belief in the afterlife independent of gender. What we're trying to say right here is that we actually want to see whether male and female, whether men and women have the same perception, whether they got the same opinion, whether they got the same perception about the belief in the afterlife. Okay, whether they got the same perception in the belief in the afterlife. Okay, because we got some people may say, oh, well, okay, I don't believe in afterlife. Okay, when I die, that is going to be the end. I'm not going to go anywhere. Okay, and there's some people that say, okay, you know what? When you die, you are likely going to go to somewhere. Okay, so that was why the General Security Survey was conducted in 1991 between men and women. And you know what? We can actually investigate whether the opinion of men and women are the same or not. Okay, that's exactly what we want to investigate right here, and that was why we call it is belief in the afterlife independent of gender. If it is independent of gender, we are actually saying in the null hypothesis there is no association. Okay, there is no association, you know, between men and women, you know, with regard to their perception, you know, about afterlife. Okay, and the alternative is actually going to say there is an association. Okay, so there is no association. No association means they are independent. Okay, that the belief is independent of gender. Okay, so the belief, you know, the belief in the afterlife independent of gender is supporting the null hypothesis. And the alternative hypothesis, we actually say that the belief in the afterlife is not independent of gender. Of course, if it is not independent of gender, not independent, that is too negative. It means it actually depends. Okay. Now, if we want to solve the problem, do you know we could address this question using a chi-square test? Okay. And how do we perform a chi-square test? We can actually perform a chi-square test by trying to measure discrepancy between the observed and the expected. Okay, you're actually going to see what we're going to do right now. Now, take a look at what I have in the table right here. Some of you may be wondering, how do I got the values right here? I think I walk you through how to go 432, 378. They are the expected. These are the observed. I'm also going to do the same thing to know. Okay, how am I going to get 150? If I want to get 150 right here, I'm actually going to use n multiplied by p. What is going to be my p? But you know what? My p is not going to be this guy again. I'm going to show you something right now. If I want to do the other one that has to do with the no, okay, so take a look at what I have here. The p that I have here is a probability of believing afterlife. Okay, now if I want to, the other one, if you don't believe in afterlife, or you are not sure of afterlife, you know, we combine that together, that probability will be 1 minus this. Okay, that probability will be 1 minus this. Okay, so if you want to find the expected number of male that will say no or undecided, you're actually going to use 1 minus this. You're going to multiply that by, I'm going to show you right now. You're going to multiply by 147. Okay, if you multiply by 147, I'm going to show you something the other time. I'll give you 1 second. If you take a look at, what is 582? The 582 that we actually use for male. Look at that. The 582. Sorry, you're going to multiply by 582. Okay, not so I'm going to use the 582 number of male. Okay, take a look at that. The 582 that I'm using is a 582 in general. Okay, the total number of male and the total number of female. Okay, that's what I'm going to use. Only that I'm actually going to be using a different probability. Okay, but the number is actually going to be the same. Okay, when I'm answering the question of yes, 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 it's that I'm going to use 0.742. But if it is no or undecided, I'm going to subtract this from 1. Then I'm going to multiply by 582 for male and 509 for female. So that if you do that, you're actually going to get 150 and 381. I'm going to say that again. Now, to be able to arrive at 150 right here, okay, like I said, we get this expectation, you multiply the number of male, which is 582, by the probability of, no or undecided. Okay, so you'll be able to get the 150. Okay, and you're also going to be able to get the 131. Is there any one of you who doesn't know how I got the values in the parentheses? Is there any one of you that need clarification on how to do that? Okay, so silence implies that you guys are good. So 435, 147, 375, 134, they are the observed values. So 432, 150, 378, and 131 are the expected values. Okay, and if I want to use chi-squared, of course, the chi-squared, this is the formula for the chi-square. Okay, it means I'm going to be subtracting the expected value from the observed value. I'm going to square that, then I'm going to divide by the expected value. And that was the reason why right here, the observed value is 435. I'm going to subtract 432 from that. I'm going to square that, and I'm going to divide by the expected. And that is what I did here, 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 and here. Okay, so when I do that, by the time I sum that together, and that is going to give me, this is going to be the chi-square statistic value. Okay, this is a chi-squared statistic. Okay, now I believe you understand how I figured that out. Okay, are you guys hearing me?
Yes.
Okay, does that mean you guys are good? Is there anyone who have a trouble time getting what I'm doing right now? Is there anyone? I can actually go back. Okay, I can go back. I can repeat myself. I can go back. Okay, so is there anyone who have a trouble time? Okay, so it means you guys are good. Okay, so after getting the chi-square statistic right here, so what is the next thing that I'm actually going to do? Okay, so the next thing I'm actually going to do is I'm actually going to state my hypothesis. Under the null hypothesis, what am I talking about? Okay, don't forget that I said we are testing the null hypothesis of independence, okay, versus the alternative that the proportion believing in afterlife differs across gender. Okay, and mathematically speaking, if I want to formulate my null hypothesis, I'm actually going to write the proportion of male equal to the proportion of female equal to the proportion overall. Okay, so that is what I'm actually testing. And under the alternative, I'm actually going to say no. The belief among gender is not the same. Okay, now we decided to perform the hypothesis testing using the chi-square test. Of course, we've gotten the test statistic value of the chi-squared. I think you know that. Okay, so now we need to get the degree of freedom, okay, associated with a chi-squared. And it's actually going to be the number of row minus 1 multiplied by number of columns minus 1. If you take a look at what we're doing right here, how many row by how many row, I'm going to take it back. I'm going to say it's going to be 2 rows, okay? We got 2 rows, and 2 columns, okay? Male and female has 2 levels. And of course, yes, no, or undecided, we put this together. So 2 by 2, okay? 2 rows, 2 columns. You are not going to count the total, okay? Total is not there, okay? Okay, so when you get a degree of freedom, we multiply that by that, you're going to get 1. Okay, so if you take a look at, after getting that, of course, you can check from the chi-square table, okay? We can check from the chi-square table. You're going to check 1 here. If you check 1, if you check this 1, on the chi-square table, you check 1 against alpha is 0.05, it's actually going to give you 5.99, okay? So that 5.99 is a critical value, okay? You're going to compare that value with the chi-square that we got right here, okay? Take a look at this, okay? Now the test statistic value is is less than the critical value, okay? Because the critical value, when you check 1 degree of freedom against the 0.05 level of significance, it's actually going to be 5.99, okay? And it means the test statistic value is less than, it's less than the critical value of 5.99. So which means we're going to fail to reject the non-hypothesis, okay? We're going to fail to reject the non-hypothesis using the chi-square test, okay? And what is the non-hypothesis that we are actually rejecting? I'm going to show you right now. Okay, so the non-hypothesis that we are actually rejecting is this guy here. Can you see that now? We are actually rejecting that, okay, we're going to fail to reject the non-hypothesis. That's what I wanted to say. We're going to fail to reject the non-hypothesis because, the chi-square statistic value that we obtain, I'm actually going to show you. Okay, so 0.173 is less than 5.99. Because of that, we're going to fail to reject, okay? And when we fail to reject means that, male and female, they got the same perception, okay, regarding the belief in afterlife, okay? So they got the same perception, okay? So which means that, the belief in afterlife is independent, is independent of gender, okay? The belief in afterlife is independent of gender, okay? It means, male and female have the same, they got more or less the same position, okay, on the belief in afterlife. Okay, so the next thing that I'm actually going to that I actually want to do now is that, of course, like I said, we're going to perform that. Give me 1 second. I think 5.99 that I used the other time may be wrong for the critical value. Oh, okay, yeah. If you want to do that in now, okay, sorry, this is what you're going to do. You're going to get 3.8414959. Okay, you can do that in R. You're going to write a Q chi-sq 1 minus 0.05 df equal to 1. Okay, so this is a critical value, okay? So not 5.99, okay? So you can do that in R, okay? So if this is a critical value, then you can compare a 0.173 that I talked about the other time, which is less, okay? So which is less, okay? And when the test statistic value is less than the critical value, you're gonna fail to reject, right? And you know what? You can also find a p-value. Okay, we can also find a p-value. Okay, so this is how to find a p-value. Okay, now, and look at the p-value right here is so large. And when the p-value is large, of course, it means we are also going to fail to reject. Okay, so the same decision with using the critical score. I'm going to say that again. If you want to use a critical score, the test statistic has to be less than the critical value. But if you want to use the p-value, then the p-value has to be greater than the level of significance. Okay, so you can see using the chi-square test, that's exactly we've been able to take a decision. Now, let me also tell you that that is using the chi-square test. What if we want to use a Poisson regression to do that? Okay, what if we want to use a Poisson regression to do that? Okay, then I'm going to start a model this way. I'm going to say, okay, Yij, a particular random variable that, a particular, event in a particular interval actually follows a Poisson distribution with a lambda ij. Okay, with a lambda ij. Okay, so the lambda ij here, okay, the other time I said lambda, okay, because I'm talking about Yij now. Okay, there's going to be a lambda ij. Okay, so the lambda ij, okay, will be equal to lambda multiplied by, alpha male and the gamma response. Okay, the I here is just to, it's going to be a gender effect. Okay, and so it means this is a high level of that. Okay, the J, the J is a J level of that. Okay, so this will be the response that I got. Okay, so that is what we mean by that. Okay, so the lambda ij equal to lambda multiplied by alpha male multiplied by gamma response. So here we interpret lambda ij as a Poisson rate for the cell in the ith row and jth column. Okay, I'm going to show you. I'm going to take you back now into the table. Okay, look at that. Maybe we're referring to this particular cell. If you take a look at this particular cell, it falls in the ith row and jth column. Okay, I mean the row for male and the column for yes. That's what I'm trying to talk about. Okay, so we're actually going to have the lambda ij. And don't forget the other time, getting the lambda ij, don't forget that we got the expected, okay? This is like a lambda ij for this. This is like a lambda the lambda for this. Okay, we got a different lambda because we got a different expectation, okay? 432, 478, 150, 131, they are expected values. Okay, so they are more or less like the lambda ij that I'm talking about. If I want to explain this, if I want to model this using Poisson regression model, what we used before was a chi-square. Okay, what we used before was a chi-square. Okay, but we want to use a different one now. We want to talk about Poisson regression model. Okay, and that is why I'm trying to say that lambda is a baseline rate. Lambda is a baseline rate. Okay, alpha is the main effect, and lambda and gamma here is a response. Okay, I think you can see that now, and that is the reason why we said, okay, you know what, lambda ij will actually be equal to the baseline lambda, the baseline rate multiplied by this. Now let me tell you this. If I want to use the incidence rate of COVID-19 in the United States of America, do you know that the probability of getting a COVID in different states differs? Okay, the incidence rate of COVID-19 in the state of Minnesota is different from the state of New York, and it's different from the state of Michigan, and it's different from the state of Florida. Okay, and if I also want to look at that across countries, okay, the incidence rate across countries also differs as well. And that is the way you know, when you're talking about lambda high j, you know, you are actually talking about, that is a specific incidence rate. And we're also going to have a lambda, which is a general, which is like a baseline, okay, rate, okay? So that's exactly what I'm talking about. Okay, so the next thing that I'm actually going to talk about now is this. You know, right now we are on Poisson regression model. Okay, I've introduced you to the model, and I've been able to tell you the lambda ij equal to lambda multiplied by alpha multiply, I'm just referring to what I just showed you right now. Now, talking about Poisson regression model, the outcome is a log of the expected cell count. I'm going to say that again. You know, in the logistic regression, okay, we normally talk about logit, right? We talk about the log of odds, okay? But in the case of Poisson regression, the outcome is the log of the expected cell count, okay? So the expected cell count that we got, that we call lambda high j, we're going to take the log of that, okay? Then the baseline is actually going to be beta naught. It's going to be the log expected cell count for female, okay? For female regard responding no, okay? And the beta 1 is the increase in the log expected cell count for male compared to females. And the beta 2 is the increase in the log expected cell count for the respond yes compared to no. Okay, I'm just trying to walk you through this now, with regard to the model under investigation, okay? Give me 1 second. I think there's something that I also need to show you. Give me 1 second. Okay, so take a look at, before I get into that, let me, so to be able to show you where we're coming from. Now, okay, good. This is where, okay, now this is what I want to talk about. You know, I told you the other time that if we are talking about Poisson regression model, okay, we are always going to have this one, lambda ij equal to lambda alpha male, this, okay? Oh no, I have this one now based on the data set that I'm using. And I said this guy is the expected cell count. The expected cell count has been partitioned into the baseline rate and the, and the gender effects. Then this is the response, okay? Now, and I said, we're actually going to have a log transform, because I said it's going to be the log of it, okay? And you remember in your mathematics in high school, when you are talking about product, okay, you are talking about product right here. You know, the difference between Poisson regression and then the linear regression we have been doing, the linear regression is the addition of, it's like addition of the component. But in the Poisson regression is a multiplication, okay? Look at that, this is a multiplication, okay? I'm multiplying this by this, then I'm actually going to log. And when I log, I'm going to use a law of logarithm, okay? Remember what you did in the high school? The log of A multiplied by B is going to be log A plus log B, okay? So if I take the log of this guy, I'm actually going to do, this is what I'm going to have. Take a look at this. Oh, can you see that now? Taking the log of both sides. You're going to be log of that, the log of this plus log of that plus log of that. Okay, so when you now have plus now, you have an additive stuff now, it's going to be looking like a linear model. Can you see that now? You remember that when we take the log under transformation, when we take the log, okay, we actually go to attain linearity. I think you know that. Okay, so I want to tell you now that this is the, what I have right here is looking more or less like the origin of a Poisson regression model. Okay, and when we take the log of that, this is exactly what we're going to have. And now it's looking like a linear model that I can actually call the log lambda here to be beta naught, okay, and I can call something the beta 1 and so on like that, okay. So based on that, I'm actually going to have this right now, okay. I'm going to show you something now. Now, based on what we have, we're going to have this, okay. Okay, you know, this is what we have, right? Okay, I can rewrite that as this. Look at that. I can rewrite log lambda to be beta naught, and I can rewrite this, you know, look at that. I can write that a beta 1 this and beta 2 that, okay? So looking like a linear model now, okay? I think you can see that now. Okay, so, but don't forget that the probabilistic portion of the model still remains that Yij, okay, follow Poisson distribution with this as the, you know, expected count for a particular cell, okay? I think you know that. Okay, so if I have, so this is a model now, okay, this is a Poisson regression model that I talk about. I just want to tell you, Poisson regression model is a log transform, okay? That is what I just wanted to know right here. Okay, so if I have that one here, revisiting my data set now, okay, you know, this is my data set now, the one I'm talking about, afterlife. Okay, so do you know, how do I now run this in R? You know, using the software, okay? If I want to use, you know, the idea of Poisson regression model, how do I do this in R? Okay, so if I want to do this in R, I need to first write out my count. My count will actually be observed, okay? Take a look at that. My count is going to be 435, 147, 375, 134. Okay, if you want to do something that has to do with the if you want to apply Poisson regression model, you don't need expected here. You don't need this one. In R, you don't need that. Okay, you only need this one if you really want to do chi-square, okay? Now, if you take a look at what I have right here, I'm actually going to prepare my data set to look like a linear structure. Why do I prepare my data set to look like this? Because if you look at the model, I've been able to transform the model, okay? We have something that looks like linear now. We can apply linear model the way it is now, okay? And that is the reason why my data set is actually going to be, okay, 1. You know, 1 and 1 mean male that say yes. Okay, because the categorical for male, you know, for male, I'm actually using 1. For female, it is coded 0. For yes, yes is coded 1, and then no is no or undecided is coded no, okay? So, so based on what I have here, you know, I'm able to, you know, extract a data set like this, okay? Where I got a count, I got a male, and I got it. So it's more or less like having a count, the response, and having, you know, the predictors, okay? This is like a gender predictor, and the you know, the response, whether it's going to be yes or no, okay? Take a look at that, okay? Okay, so I'm going to have that one now. Then I'm actually going to take you through how you can actually do that in R. But before you can do that in R, you need to be able to know how you can interpret what's going to be your beta null, what is going to be your beta 1, what is going to be your beta 2. How can we interpret that in case you are done? And that was why I said the outcome is the log of the expected cell count. Okay, and then the baseline, which is the beta naught, is a log expected cell count for the female responding no. Okay, for female responding no, don't forget that we coded female as 0, and we coded you know, no as 0. Okay, and don't forget the way we normally interpret the intercept. Okay, the intercept is assuming that the predictor is 0. Okay, now the beta 1 is going to be the increase in the log expected cell count for male compared to female. And the beta 2 is actually going to be the increase in the log expected cell count for the response yes compared to no. Okay, I think you know that now. Now, let's go through the results. Now, take a look at that. If I want to do that in R, this is the code. Oh my God, this is the code. Can you guys see the code right now? Can you guys see the code? Okay, thank you for that. Okay, so count. Count. You saw the count. You saw it the other time. Count is actually this: 435, 147, 375, 134. And please, you have to make sure it's in that order. Okay, take a look at that. Okay, can you see that? 435, 147, 375, 134. Okay, you can see that order. Okay, can you see that now? Okay, so when you write count on male plus yes, okay, this is looking like having a gender as a predictor and having the whether they're going to say yes or no as a predictor. Okay, so that is that. Okay, then you're going to write family is going to be Poisson, not binomial. Okay, the family here is actually going to be Poisson, not by. If you put binomial, it's not going to run. Okay, so this is the code to run a Poisson regression in R. Oh, this is the result that I have right now. You can see the beta naught, you can see the beta 1, you can see the beta 2. Okay, so how do I interpret that? And that is the reason why I said if you want to interpret that, this is what you're going to do. Okay, the baseline beta naught is a log expected cell count for female responding to no. Okay, so that's how we can interpret that. Okay, the beta naught, the beta 1, and the beta 2. Okay, now, so I think you can see that now. Okay, so everything is going to come out with that. You're going to have the residual deviance, you're going to have the AIC, and so on like that. Okay, and you can going to have a p-value. And let me also tell you, okay, the test statistic value is going to be z, just like in logistic. It's also going to be z. Okay, it's not going to be t. Okay, these are the estimates, these are the standard error, and these are the corresponding p-value. Okay, I think you can see that now. So these are the corresponding p-value. Now, there is something that I want you to notice. The other time when I used a chi-square, what was the decision that we took regarding whether regarding the belief across gender? Okay, the decision we took, we failed to reject the non-hypothesis. I think you know that. Okay, now if you look at gender, if you look at the gender here, okay, the gender here, you get a 1 star because it's 0.05 uh, is not significant, okay, because it's less than 0.05, the p-value here. But at 1%, okay, if you let me tell you something. If you look at 0.02, 0.02 is less than 0.05 or greater than 0.01. So at 1% level of significance, the gender is significant. Okay. Sorry. At 1% level of significance, the gender is not significant because the p-value 0.02 is greater than 0.01. But at 5% level of significance, 5% level of significance, 0.02 is less than 0.05, it is significant. Okay, I think you know that. And that was why, a star here, it represent 1 star means at 0.01. Okay, I think you can see that now. And and when you 3 star means at any level of significance, it is significant. Okay, that's why you got a 3 star. I think you can see that now. Okay, so and this is trying to show that opinion differs, right? Opinion differ. There's a difference between yes, the difference between the number of people that say yes and the number of people that say no. Okay, now so if I want to write the model out now, this is the way I'm going to write the fitted model in a Poisson regression model. Okay, where do I get 4.88? I'm going to show you right now where I got 4.88. Okay, so I got 4.88. Look at that. That is a beta knot. I think you can see that now. Okay. Now, if you 4.88, so can you see 4.88? Okay, and you can actually see the beta 1 and the beta 2 is 0.134, 1.06. I'm going to show you right away. Okay, can you see that? It's 0.134 and 1.0. So this is the combination of what we're using in the model. So in case I give you something like this and I ask you to, and it's a Poisson regression model, and if I ask you to write the model for me, okay, if I ask you to write the model out, this is what I'm expecting from you, okay? So this is a fitted model, okay? This is how to write the fitted model. I think you get that. Oh, so I here, what I put here is an indicator, okay? That's what you're going to have, indicator that, okay, or, this is categorical, okay? That is what we use that to represent categorical, okay? To be able to tell you we got 2 levels of gender and we got 2 levels of the response, okay? Somebody said, since Poisson distribution approximate the binomial distribution, does this mean the count is independent? I.e. there is no interaction between counts? It doesn't mean that, okay? When Poisson distribution approximate binomial, what I'm just trying to tell you is that how you can actually go from binomial to Poisson distribution, okay? How you can go from binomial to Poisson distribution. Remember the other time, when we're working on linear regression model, the probability distribution of the response variable given predictor in a linear regression model is normal distribution, okay? Now, remember that by the time we want to talk about the probability distribution of a categorical variable, okay, given the predictor was no longer normal, we transform the model by going from normal distribution by, going to binomial, okay? So what I told you before is that we can actually have a way to go from binomial distribution to Poisson distribution, okay? And to go from binomial distribution to Poisson distribution, then the sample size has to be large and the probability of the characteristics of interest has to be very, very small, okay? Because why do we need Poisson distribution? We need Poisson distribution because Poisson distribution is a probability distribution of a Poisson random variable, okay? And Poisson random variable is a count, okay? That is what we use in Poisson regression model, okay? So that is exactly what I'm talking about. Okay, so you guys can see the model right now. Okay, this is the model. So this is how to write out the model. Okay, so if is there anyone want to ask question? Okay, so this is the way the model is actually going to look like. Okay, now if I have this model right now, so what is the next thing for me that we can do? Of course, the next thing we can actually do is to just go way of interpreting the model. Okay, so now take a look at this right now. We had a fitted model. I think you know that. We have already plugged in the values of beta 0, beta 1, and beta 2 into the model. Okay, then you know that we can actually predict, values. Okay, so for females responding yes, okay, for female responding yes, okay, so we can find the log of the expected count given female and the female say yes. How am I going to do that right here? Okay, so I told you this is an indicator. To male equal to 1, I'm talking about male, and male equal to 0, I'm talking about female. I'm actually going to plug in 0 into here because I'm talking about female. You remember what we did before, okay? So I'm going to put 0 here. And yes, it's coded 1. Then I'm going to put 1. Okay, Don't forget that my beta naught is 4.88, my beta 1 is 0.1434, my beta 2 is 1.06. Okay, so if I want to get this now for female saying yes, or for female, I'm going to put 0 here. For yes, I'm going to put 1. Look at what I got. What did I get? Well, 5.94. Okay, the 5.94 here is the log of the expected count giving female and yes. This is it. Okay, and if I want to get the one for male, okay, for male, of course, you know what I'm going to plug in. I'm going to plug in 1, you know, 1 for male and 1 for response, because the response is yes. And you know that at the same time, I can actually ask you to find female saying no. Okay, if you want to find female saying no, no and no, of course, you know what you're going to plug in for no. Is there anyone who need a clarification on how to figure this out? Is there anyone? Is there anyone? I believe you guys are hearing me, right? Can you guys hear me? Okay, so silence implies that you guys are good. Okay, so this is it. Okay, very good. Now the next thing I'm actually want to show you now is I've walked you through the model. Now, how do I interpret female responding no? I told you. So female responding no, I coded female as 0, I coded no as 0. It's going to be 0, 0. I'm going to plug in 0, 0 into the model, and that's going to be 4.88. Take a look at that. Something is going to surprise you right now. 4.88 right here. Does that look like the intercept? Let's check. Oh, that is the intercept. I told you before. Okay, what I put in the control group, I put female and, you know, I put female and the responding no in the control group. And that is actually the intercept. Okay, 4.88. Okay, so what I just told you right now, take a look at that. So that is the reason why okay, so, and that was the reason why we got 4.88. So automatically, it's going to give you the value of the intercept. Okay. Now, you can also find male responding no. So male responding no, you're going to plug in 1 into the model, you're going to plug 0, okay? You got that, okay? Now, after that, do you know that we can actually use a fitted model? You know, we can actually get predicted value for count in each of the 4 cells. Okay? In each of the 4 cells, we can actually get a predicted values for counts. We know we have the observed value for count, but we can also, using the Poisson regression model, okay, using the fitted Poisson regression model, we can also have compute a fitted model. Okay, I mean the fitted value for the expected count. If you want to do that, it's actually going to be, if I want to find for female responding no, what is the predicted value for count? For count is like how many numbers of women that will respond no. Okay, so it's going to be expected count giving female no. And you know what? Female and no, you know, we said 4.88, we're going to do the exponential raised to power that. You remember when we do the logistic regression? Going to be exponential raised to power that. The exponential raised to power that will be 131. Okay, and if you want to go back, you're going to see, I'm going to walk you back and see what I'm talking about. Okay, so this is where, you know, we got 131 the other time. When we're doing a chi-square, right? It's still, look at that, you're going to get the same value. Okay, so what I'm trying to tell you right now, if you want to figure that out, okay, the predicted values for counts, okay, so for female responding no, it's going to be the exponential raised to power the beta naught. I'm going to say that again, exponential raised to power the beta naught. Why do I get that? Okay, because this guy equal to 0, this guy equal to 0, the whole things will be 0 right here. What am I going to get? I'm going to have log of this equal to beta naught. Log of this equal to beta naught. If I solve for lambda ij, okay, if the log go to the other side, it's going to be exponential raised to power beta naught. And that's why I got this. Okay, I'm still using this model. Okay, but right here, now, the beta, you know, this is 0, this is 0. What I have is 0, what I have is 0. So I'm only going to have log of lambda ij equal to beta naught. And what I'm looking for, you know, the predicted count is lambda high j. Okay, the lambda high j is the predicted count for a particular cell. Okay, so when I have the log of that, when I want to, after that, I'm going to be lambda ij equal to exponential raised to power beta naught. And that's why I have exponential raised to power that. So similarly, I can also find the expected, you know, the predicted values of count for male responding no. Okay, for male responding no, it's going to be expected count giving male, you know, no. Okay, of course, for male responding no, it means I'm going to use this one because it's going to be 1. Responding no, I'm not interested in this. Okay, I'm not going to use a beta 2. Okay, so I'm only going to have 4.88 plus 0.1434 times 1, because the 1 here is talking about May. For no 0, the you know, this is not there. Okay, if I want to find a lambda high j now, it's actually going to be exponential raised to power beta naught plus beta 1, whatever I have it. So that's how you have this. Okay, so that's why you got this one here. Okay, can you see that now? Okay, so the next thing that I want to talk about now is so you can also find, similarly, you can find the expected predicted count values for, you know, this is for female responding yes. You're still going to use the same model. Okay, female responding yes. Okay, female, the beta 1 is not going to be there because it's going to be 0. You're only going to be using the combination of beta naught and the beta 2. Okay, and that's why 4.88 plus that. Okay, exponential of that will give that. Okay, for male responding yes, of course, for male responding yes, you're actually going to use all of that. Okay, so all of that is going to be 1. This is going to be, so you're going to, so that's why for intercept 4.88, and this is going to be like 0.134 times 1, which is this guy, and 1.106 times 1, which is this. Okay, and the exponential of that, I will give you 432. If there's anyone who want to ask question, you know, you can ask. Okay, so okay, so by fitting the independence model, okay, we are talking about the afterlife coefficient. By fitting the independence model, we force the relative rate of responding yes versus no to the question of belief in afterlife to be fixed across male and female. And deviation for the independence model suggests the proportion of those believing in afterlife differ by gender. Of course, we're trying to see, you can see that from the output that we got. Okay. Now, the next thing that, excuse me. Okay, the next slide right now. Comparing model fit in R with our fit by hand. Okay. What we did before, you remember we did it before, right? When we're dealing with a chi-squared, that we calculated the expected circle by hand. I think you remember that, because before first get the probability of yes, okay? You remember that we got a 0.7 something, and later, we later obtain the expected counts by hand. I think you know that, okay? So, and then the values that we got are exactly the same value that we got using Poisson regression, okay? I think you know that, okay? So just to tell you. Okay, so right here now, what I have now, this is how you can interpret the values, okay? The regression parameter values, okay? The beta dot of 4.88 is a log expected count of female responding no. And that is a baseline group, okay? I talk about baseline group, okay, which is more or less a control group, okay? So the beta 1 is a difference in the log expected count comparing male to female, okay? And the beta 2 is the difference in the log expected count for yes responses compared to no responses, okay? I think you get it now. So this is how you're going to interpret that. Okay, so, and I've been able to explain each of that to you under the independence model. The expected value of beta naught equal to that, which is the expected count for female responding no, the baseline group, and the expected value of beta 1 alone, which is 1.14, is a ratio comparing the count of male to female, okay? Comparing the count of male to female, okay? Comparing the count from male to female means, since this is greater than 1, it means the number of male, okay, is actually greater than the number of female. That's what we're talking about, okay? Now, look at that. This beta is equal to that is the ratio of the number of yes responses to no responses, okay? So which means, if you want to look at this as the odd ratio is greater than 1, it means there's likely to be more on the yes responses than no. Okay, so there's something I want to show you right now. So relation to other types of regression, of course, I think I've explained that both logistic and Poisson regression model are type of linear models. Both extend the idea of linear regression with a continuous outcome to binary outcome. Binary outcome, we use logistic regression. Count data, we use Poisson regression. And you know what? You also need to know for logistic regression, I can ask you about the link. What is the link for logistic regression is the logit. The link for Poisson regression is the log. The link for Poisson model, we also call that, it's also a Poisson model is also called log linear models, okay? Because it's log linear model because you have the log of the lambda ij. Don't forget that initially we got a multiplicative model. Okay, it was multiplicative model. We got a lambda ij equal to lambda multiplied by alpha multiplied by gamma. Okay, we take the log of that, and that was why we call Poisson regression model is a log linear model. Okay, it's a log linear model. Okay, so talking about the link, for linear regression is identity, okay? I'm going to say that again. Talking about the link, for linear regression is identity, for logistic regression is logit, for Poisson regression is log, okay? And that's why I put that here, okay? For the, for three type of regression, for linear regression, the distribution of the response is normal. For logistic, it is binary. Okay, which we call binomial distribution. For log linear, when I say log linear, of course I'm referring to Poisson regression model, okay? And the link for linear regression is identity. The link for logistic is logit. The link for log linear is log, okay? And you know what? What we have right here is a link function, okay? Because every model has a link function, okay? If the f of mu equal to mu, then we're referring to identity, okay? We're referring to the linear regression model, okay? If the logit of P equal to the log of odd ratio, of course, we are referring to the logistic regression, okay? If we take the log of P, okay, we are only referring to the Poisson regression model, okay, which is also called the log linear model, okay? So I just wanted to know that, okay? Okay, so a regression model for count data, okay? This is just when you have a contingency table, okay, where we got where data set are cross tabulated, okay, just like what I showed you before, where you got a row and a column stuff. Of course, you know, this is a model, okay? The log of the expected value of Yij, which is equal to the log of lambda ij, okay, is equal to this, okay? What I have right here is the general formula of a Poisson regression model that we also call log linear model, okay? Log of that linear. This is linear because we have been able to have something plus something plus something, okay? So that is that, okay? And when we make use of the chi-square test, of course, I show you the formula the other time, okay? And I show you the distribution of the test, okay? Just to remind you what we have been doing since morning, okay? Now, and they use under the model, of course, I walk you through the model. You can see the model, okay? And then I told you the lambda is a baseline rate, okay? The baseline rate, okay? So which is it? Which is that, okay? I think you can see that now. Okay, so I'm just trying to walk you through what we've been able to do, okay? And I also talk about the interpretation, okay? This is the model. How do we interpret? We got the alpha high, we got the gamma j. Okay, the alpha I is a rate ratio, okay? The effect of being in row high compared to the baseline, okay? And the gamma j, of course, is the rate ratio, which is the effect of being in column j compared to the baseline, okay? And of course, we can actually find the rate ratio, okay, which is the factor by which the baseline is multiplied to get the rate or the expected cell count that I've walked you through before. Okay, so like I said, another name for Poisson regression is log linear, okay? So I think I've walked you through something like that today. And given observations and covariates, okay? So we have the yi and the sij, okay? That have it two, that can be categorized, okay? Where you got a cross tabulation for that, okay? So the systematic component of the model is actually going to be this, okay? So take a look at that, the log lambda I, the beta naught, that depends on whether you have, you have it depends on the number of predictors that you're actually going to have in the model. At time we could have more than, the categorization that I walk you through right now is just 2 by 2, okay? We could have a 2 by 2 by 3 and so on like that, okay? So just to be able to let you know. And of course, this is the distribution of a count data, okay? The distribution of a candidate, the distribution of a candidate be given any predictor is Poisson, okay? With a lambda high as a, the rate parameter, okay? Okay, so this is another example that I want to walk you through now. Okay, today I'm actually going to stop at 3:30, okay, in the next 11 minutes, okay. I'm going to have an extended, for those of you who have lecture, you can opt out. But like I said, immediately after this lecture, I'm actually going to attach the material, okay. So we want to have another example right now. Customers at a lumber company, okay. The outcome is the number of customers visiting store from region, okay. Like I said, one of the example of it, this is an example of a count data, okay. But this time around, we got 3 predictors, okay. We got, not 3 predictors, we got 5 predictors, okay. X1, the number of housing units in the region. X2, average household income. S3, average housing unit age in the region. S4, distance to nearest competitor. S5, average distance to store in miles. Okay, you know, let me first explain this to you right now. Some of you may be wondering, why is it that I can't use a simple linear regression model for this data? Okay, you can use why is it I can't use multiple linear regression model for this data? Okay, because this is a count. Okay, this is a count. Okay, and we believe that, you know, if you want to, for me to visit a store, you know, I have to consider, you know, the average distance to store in mind. Okay, and you know, I can remember at times when I'm driving or when I'm in my house. Okay, and I want to go to the grocery store. I can, maybe I want to go to Walmart. I can put, okay, Walmart near me. Okay, I can put on Google Walmart near me. Okay, so at times, you know, the distance to the store is very, very crucial. Okay, so then the distance to the nearest competitor. Okay, if I have different kind of store around, okay, so the distance to nearest competitor will also determine. Okay, then another thing that determine, you know, customer going to store will be average housing unit. Okay, age in region. Okay, the next thing is the average household income. Okay, and the next is the average. The number of housing units in the region. We actually determine the number of customers that will actually visit the store in the region. Okay. Now, based on the variables we have here, we're going to consider 110 regions. Okay. So our n is actually going to be 110. Okay. Now, this is going to be the data set that was collected over the 110. Look at that. Okay. In the store in the region 1. Okay. So 9 customers. And in that region, they got 606 housing. And this is the mean income. This is the mean age, the competitor, and the store. Okay. So these are collected over, if you take a look at what I have, the experimental unit is actually going to be 110 regions. I think you get that now. Okay. So this is what we have. Take a look at that. Can you see that now? Okay. So if you basically look at what I have right here, we can actually fit a Poisson regression model for this data set as well. Okay. You know, it is not only all the time when you have a categorical, or it's only all the time when you have a cross tabulation. Okay, we can also use Poisson regression model for a data of this nature, a situation where they refer to the customers, you know, the response variable as a count. The moment it's a count, okay, then you cannot fit a multiple linear regression model for this. Okay, because some of you may be thinking that, oh, but my response variable is quantitative. Why can't I fit a multiple linear regression model? But because this is a count data, okay, and that's why you're going to use a Poisson regression model. Okay, now if you take a look at what I have here, I said the customer count distribution is clearly not normally distributed. Why? Okay, how do I know? Somebody may want to argue it out. Why can't I use linear regression? But you know why? There is always going to be an assumption underlying the use of a model. So when you try to find, when you do the distribution, let me tell you something right now. Did you know that when you plot the histogram of the response variable, the only one of the conditions for you to use a linear regression model is that the distribution of the response variable has to be normal. But when you take a look at this, when you try to draw the histogram for customers, which is a count, it's not going to be normal. Okay, and that is the first thing you need to do for you to be able to know whether you're going to fit a Poisson regression model or a linear regression model. Okay, now that's exactly what we do right here. Look at that. This is skewed. This is not normal, okay? This is the histogram of the customers, okay? So this is skewed. And you remember the other time I showed you that Poisson distribution is skewed. So this is more skewed like a Poisson distribution. And that is the reason why linear regression will not work well. Okay? And what is going to work is actually going to be Poisson regression, okay? Which we also call log linear regression, okay? Now, and that is the reason to be able to know, that is what makes us to know, okay? Now, the next thing that I'm actually going to show you now, since it's a log linear regression, since a log linear model, okay, take a look at that. This is going to be the model because I got 5 predictors, 1, 2, 3, 4, 5. And don't forget, I'm actually going to write log lambda high equal to that. Log lambda high equal to that. So this is Poisson regression model. And it's also the same thing as log linear. You can say log of the response, okay, against that. But you are not only logging the y. You know, some of you may be wondering, what is the difference between what this and what we did in the power transformation? What we did in power transformation, we only take the log of the response. But right here, we are not taking the log of the response. We are taking the log of the incidence rate, the lambda high, okay? So when you run this in R, okay, like I said, if you take a look at if when we do the distribution of that, this is what we have to tell us that this is not normally distributed. And when we run that in R, okay, this is going to be the result. Okay, this is going to be the result. The beta 0, the beta 1, the beta 2, the beta 3, the beta 4, the beta 5. Okay. Now I'm going to show you the code how to do that in the net. Okay, yeah, the code is here. Take a look at that. This is the code. Okay, this is what you're going to write as a code. Okay, customers on housing. In the normal code, I go no matter, but you need to write lumba.glm. Okay, lumba.glm. Okay. You don't necessarily need to write this. This is just the name of the model. You can use anything here, but it's just GLM. Okay. Then don't forget to write Poisson and look at what we have. This is the output. Okay. Can you see the output now? Okay. This is more appropriate than running a linear. So what I'm showing you, what I'm teaching right now is just the log linear model in R, which is a Poisson regression model in R. Okay, the estimate of the parameters here is actually if you take a look at what I have here right now, 2.94, 6.05. I'm going to show you now 2.94 and stuff like that. You're going to see that here right now. Can you see that now? So you can see you got 2.94 and so on like that. Take a look at so I think you can see that now, okay? This is 0.0000 something, okay? I think you can see that now. So the estimate, the fitted model now is actually what I put here, okay? The fitted model is actually what I put right here, okay? Where you'll be able to measure the contribution of the housing, of a particular housing, of the income, of the age, of the competitor, and the distance to store, you know, on that, okay? Okay, so having know that, I've walked you through how to get that. Of course, you're actually gonna, this is part of the output. Okay, you can see how you can tell on the significance. You know, right here, intercept is significant, housing is significant, income is significant, age is significant, but not at 5%. Competitor is significant, store is significant. Most of the parameters here are highly significant. Okay, I think you can see that now. Okay, so if that is that, do you know that you can interpret the beta notes based on this data set? Okay, so we interpret the beta note to be 2.94. That is a baseline log expected count. or log rate in the group with all covariate housing income, a distance to nearest competitor, and average distance set as 0, okay? So you're working on the intercept, okay? And if you want to know the expected number of counts of customers in the baseline group, you're actually going to do the expectation of the beta naught, okay? So which is the 18.9, so which means about 19 customers are actually predicted to be in the baseline group, okay? And you know what? The baseline value does not make any sense, okay? Does not make any sense, okay? So, you know what? And like I said, it may be helpful to center our covariate, but this is not a big deal, okay? Because if you don't care about the baseline, because the primary inference is about the increase with the respect to the covariate, okay? So you don't need to worry about the scaling, okay? Now, lastly, today you can actually this show you how to interpret the parameters. Okay, this particular value here is just the increase in the log expected count or the log rate ratio comparing the districts whose number of housing units differ by 1, adjusting for the other covariate, okay? And this one is talking about the rate ratio comparing districts whose mean housing unit differ by 1, adjusting for the other covariate, okay? And so that is what, so if you take a look at this, this is the beta one, and this is the exponential of that, okay? You actually want to know the number, okay? So then if you look at the next one now, so this 100 multiplied by beta 1, it's actually going to give you which is the rate ratio comparing district whose mean housing unit differ by 100. Okay, that was why, the one here is by 1 times that, okay, 1. Okay, that was why units differ by 1. That was why I multiplied this by 1. But if I want to talk about unit differ by 100, I need to do 100 multiplied by that, okay? So what I'm trying to say is that keeping other factor constant, a 100 units increase in housing units will yield an expected 6.2% increase in customer count, okay? Now, where do I get 6.2%? Where did I get that one from, okay? If you multiply this by 100, you're actually going to get 106.2%. Okay, so 106.2%, when you subtract that for 100, you're actually going to get 6.2%. That means you got 6.2% increase. So you get that now? Okay, so okay, so for the beta 2, you're going to do the same. Look at the beta 2. Okay, so we interpret beta 2 equal to that to be the increase in the log expected count or the log rate ratio comparing districts whose mean income differ by $1, okay, adjusting for other covariate, okay, as you can see that now. And if you want to know the expected, okay, you know the expected value of the beta 2, which is this one. This is the relative rate comparing region whose mean income differ by $1, adjusting for other covariate, okay. So I think you can see that now. So these are interpretations, okay, of what we have done, okay. And the same thing also go to every other one, okay. So, and of course, you can tell the significance about the parameter, okay. So what all this is just, okay, let me quick, I'm going to finish that, okay. Let me finish that. So here, I said, although our reported estimate of beta 1 is very small, so is the standard error, okay? If you go to the table, the beta 1, I'm going to go to the beta 1 now. Now, look at the beta 1, okay? The beta 1 is very, very small. This is 0.0006, very, very small. And also the standard error is so small, but it is significant, okay? We also experience that in linear regression, okay? A situation whereby the estimate is very, very small, but it's still significant, okay? And that's exactly what I'm trying to talk about. Give me 1 second. Okay, so that is what I'm trying to talk about right here. Okay, so the Z statistic reported is 4.26 with a p-value of that. Okay, and we can conclude that there's a statistically significant association between the customer count and the mean housing unit in the region. Okay, so just to be able to tell you, and of course, the formula we have used is a Z statistic, which is the ratio of the beta 1 to the standard error in that very table. Okay, I think you know that, right? Okay, so do you know that similarly, you can also, okay, okay, I think yeah, you can also look at the expected value of the, 10,000, what is the meaning of this? Okay, what we want to do, okay, initially we normally say exponential is per beta 2. Why do we put a 10,000? Okay, it depends on the unit increase. Okay, here, the rate of comparing region whose mean income differ by $10,000. So I'm going to use 10,000 to multiply that before I take the exponential. Okay, that's exactly, that give me a 0.889. So that is a relative rate. Okay, so keeping other factor constant. Okay, the relative rate comparing regions whose average income differ by 10,000 is that. Okay, and for a 10,000 change in an average income, okay, we will predict an 11% decrease in the rate of customer visiting the store. Why? Where do I get 11% from? Okay, if you take a look at what I have here, if you multiply by 100, that's going to be like 89%. Okay, if you subtract that from 1, okay, if you subtract 89% from 100, that will be 11%. Okay, so it means for a $10,000 change in an average income, we will predict an 11% decrease in the rate of customer visiting the store. Okay, and that is the reason why average income, change in average income, affects the change in the rate customer visit the store. Okay, I want to tell you, even in the, despite the fact that we're in the middle of pandemic, when President Trump, gave a stimulus package to Americans the other time, you can see that the rate at which, customer visit a store, actually increases, in that interval of lockdown. Okay, I think you get it now. So that's what I'm trying to talk about right here. Okay. Okay, so and you can also do the confidence interval for the beta 2, for all the parameters. Okay, so let me tell you, are you guys hearing me?
Yes.
Okay, so you can also do the confidence interval for the beta 2, beta, and so on like that. Okay, and this is the formula to do the confidence interval. Of course, you just need to use the value of the beta 2. Okay, 1.96 is just trying to tell us we are working on a 95% confidence and the standard error. Of course, you're going to take the standard error of beta 2 from the arrow output. Okay, and at the end of the day, this is the range for the beta 2. Okay, and if this is the range of the beta 2, you can also find the odd ratio for that. Okay, the odd ratio is going to be exponential raised to power the interval. Okay, exponential raised to power this, exponential raised to power that. Okay, so that you're actually going to have this. Okay, so when you have this now, okay, so if you want to talk about the $10,000 increase, the 10,000 units housing unit that I talked about the other time, we can talk about the interval for that. Okay, the exponential of 10,000 multiplied by that, it means this is going to be the rate. Okay, the rate, excuse me, the rate is going to be between a 0.854 and a 0.927. Okay, so this is going to be the rate. Okay, the other time we were doing this, we only got one as one value for rate, but with the confidence interval, we're going to get like, okay, you're going to lie between this and that. Okay, so that is what we have there. Okay, so today we've talked about Poisson regression, and that I've been able to tell you is a special case of a generalized linear model, and so it is closely related to the linear and logistic regression model. Okay. Lastly, before I go, Okay, so that is the interpretation that I just talked about. Okay. Let me read my chat if somebody has a question. Will you post the material on Canvas after class? Yes, immediately. I'm going to post material immediately. Okay. I'm going to post the material immediately. Okay, so when I have the exponential raised to power that I said before, okay, so what we're trying to say is the 95% confidence level for the relative rate of customer visiting the store. It's actually going to be this for a $10,000 increase in the average income for the region, okay? So and based on this model, if we are going to choose a location to build a new store, should we choose area with a higher or lower income? Does it matter? Okay, I think that's a question that you are actually, for those of you who want to build a new store, and you know what, what you are able to get right here, because based on what we have done today, you can see they are highly significant. Okay, all the predators here are more or less significant. It means they need to be put into consideration, when you want to build a new store. Okay. Okay, so is there anyone? This is going to be the end of the lecture today. Immediately, I'm going to upload this material. Like I said, this particular topic that we did today is very, very essential. Okay, so this is a Poisson regression model. Okay, is there anyone who want to ask question